Today I want to talk about a different topic, or at least introduce another kind of thing that if we're serious about our programming languages, then we should care about this. And it has to do with some details on how would you actually implement these things. A little bit. I mean, there's a lot of details that go into it, but I want to start by focusing on this rule that we've seen, which is the compatibility of the operational semantics with evaluation contexts. All right, so this is the rule which says I can reduce in an evaluation context if I see a reduction. So here I'm writing R to mean an actual reducible expression, which people shorten as redex. Like I actually apply a rule here. And I step to N, which means that I can do that step in any evaluation context. But what does this mean if I were to implement this rule exactly as it's written? Like, what is the actual computational content of this rule? Right? Because when someone hands me a term, it doesn't come in this form. Right? I instead get some I get some original term M, and I have to figure out how to decompose it into an evaluation context surrounding something that I know how to reduce. All right, that's what that means. And so pictorially, what do I have? So again, this is my big syntax tree. And someone just hands me this big syntax tree M. And as you remember from when some of the industrial speakers like from Jane Street came in, this could be millions of lines of code. And now I have to figure out, what do I simplify, right? So I start from the top. I start from line 1. And I start digging through my code, and I'll kind of traverse in some pattern, maybe down, and then I come up, and then I go down and up and go all around. And then eventually, I find a reducible subtree R within this giant context. And then the context is my E. And so what does this rule say? After you've started from the top and traversed, 3 million lines of code, I find something to do. So let's do it. And now we update the tree, and maybe it's now some other thing. So I replace R with N, and if you're really lucky, you can do this in place. If not, I have to follow my path all the way to the top of the tree. If we're kind of doing this we're implementing our language in purely functional languages, I can't do this in place. And then I get back to the top of the term N. That's what this says, is replace R with N, and go back to line 1 and start it all over again. Right? So this is the program model of, in order to run your program, read potentially all of the code, find the one line where you can do a tiny step of change, then forget what you were doing and start from the top on every step. Right? So the performance is essentially on the order of however many steps it takes to compute my program times the lines of code, but actually worse because these operations can make the code bigger, so it's not even bounded by that. It could be even worse than that. So this is not a very tractable model for running our programs. So I want to introduce one of the techniques that are something that has a little bit more reasonable performance, right? And kind of is meant to capture in a less painful way what would happen in a realistic kind of machine-like implementation, which is why this is called an abstract machine. All right, so these are going to be abstract machines. And they typically solve a number of problems. There's another problem, too, aside from just the traversal, right, which is that substitution is a terrible model for how to do things. I mean, it gets you the right answer eventually, but what's the problem with beta reduction, right? If I have a function, and this function might use x many times, I mean, it could use it 3 times, 20 times. There's no real bound on how many times I refer to the parameter of a function. And then I apply it to something big. What do? copy and paste that really big thing. And so suppose this is like 5 million lines of code. So copy and paste 5 million lines of code however many times I use it. So this is why things get really absurd. So this is big 3 times. So both of these are huge problems if you want anyone to see what the answer to your program is, right? So I want to look at sort of a super basic, simplest version of an abstract machine that I know, and then start doing some interesting things with that. All right, so what is the simplest form of abstract machine? And I'm going to start by just focusing on this part, right? This search for a redex. Because what will happen often, and what's usually the place, is when I do a step here, the next step is probably really close by. So instead of starting back at the top and retracing my steps, I may as well start from where I left off and keep going. That's the basic insight. And so that means that we have to remember where we are when decomposing the entire program into the evaluation context and the thing that I'm reducing, and kind of take this search path seriously. Right? So that's going to be the idea. We're going to take our search for a redex to be part of the computation itself, and then we're going to keep track. We're not going to lose track of that information. All right? And so, like I said, I'm going to do the simplest possible machine. I'm going to leave off some of the other details. So let's just focus on functions as the most interesting part. And so what are the 2 operations, right? I could have a application, or I could have the lambda, right? So suppose I have an application. And so what do I do? So if this was a lambda, then we can apply the beta rule, and that's really easy. But this is, statistically speaking, probably not a lambda, right? It's probably something else, right? And then what should I be doing? I should be working on the m, right? So that means I need to shift my focus from this term, m applied to n, to just the m itself. And so I'll do it this way. Right, so I'm going to have now my machine configurations. I think I used a K in the notes. Yes, good. So essentially, this K is going to be a data structure, which is keeping track of my search path through the evaluation context. So it holds the same information as E, but it's kind of inside out. That's the intuition, right? Because we're going to be doing it from the point of this dot in the middle. So this is kind of the most recent bit of the evaluation context we'll see. And then if you go backwards, right? So has anyone here heard of a zipper before in functional programming data structures? This is basically a zipper for evaluation context. That's all we're doing. We're zipping our way down, and then we can zip it up again. All right? So what I want to do is say, OK, if I'm computing the application m applied to n, first compute m. Right, so I'm going to shift my focus of the machine to m, right? But what was I doing, right? If m happens to be a lambda or eventually becomes a lambda, right, what do I do next? I have to remember I'm applying it to the argument n. So I need some way to represent that, and I'm going to do that with a stack punctuated by this little dot in the middle. So this is the application. This is saying, whatever this is, apply it to n, and send the result of that application to K. Right? I'm just keeping track of the information. I need some data structure, and the obvious data structure is a stack. All right, so we just need some punctuation to separate these things. OK? So that's the first step. And then the second step is what happens. So if m is a lambda, right, I should be doing a beta reduction, right? And so what happens there in the beta reduction, I would say, well, this is a lambda applied to an argument, so do the substitution, right? So since I've kind of separated them and moved them apart, I'll say if you find a function and it's next to the call stack that came from an application, what should we do? We should plug n in for x. Right? Because in some sense, these 2 forms are basically the same, but I've drilled in my search, so I just remember that I'm right there. All right, so I want to plug in the argument for the parameter x. And then where do I send the results of the function? To k, right? So I'm not starting way back at the top. I'm continuing off from k. And maybe I have to dig in through here, but I am going to have to send the result to k, so I don't have to dig through again there. So let us do that. So for now, I think to make sure we end on time, because that's really important today, I'm going to skip the issue of substitution. We're just going to do substitution. If you want to fix this problem, does anyone know how to fix the substitution problem? Call by need. That helps. De Bruijn indices. So these are interesting answers, which is not quite solving this problem, but they're solving other interesting problems. What's other things? Yeah. Environments, right. So rather than do what I'm about to say, so usually people will complain, this is correct. Just use substitution to plug it in, but it's going to blow up that term. So if you want to fix this, well, you can add environments, which is really standard, and I have some notes, some details in the notes if you want to see how that works, if you haven't seen that before. I'm going to skip that detail so we can do much more fun stuff. But just to kind of point out, this also has a performance problem. And, well, aside from that, what's the goal of these abstract machines is, well, two things. So this is enough for now, right? And unlike this rule, the amount of time it takes to figure out and decompose and like understand what is E and R is unbounded, or rather it's the size of the input term, right? So this could take a long time. These rules, to know if this matches, is constant time. I look at the syntax tree, and the top node is an application period. That takes one step or maybe two steps, depending on how you implement it. Or it's lambda, and my decision is done. So this is a constant time matching. So these are axioms, right? The rule immediately applies in a fixed number of steps, or it doesn't. And then if you have environments, then the amount of time it takes to execute the rule is also kind of bounded by some reasonable size. It's not dependent on the source term, right? So that's why we do that. And so this is kind of the point of the abstract machine, is to give a reasonable cost model for how long does it actually take to run these for real. That is much more accurate than this very abstract notion. And it gives you some hints on how you would implement this, right? So if I were to actually implement my little lambda calculus language, I would not do that. It would actually be very hard to do, but I could set up an interpreter, which would have my term, a continuation, and if we're going to be very fancy people, an environment. And then each step does a little bit of work. And we're just kind of moving some data around between different data structures, right? Kind of like an abacus. OK. So this is the very basic machine, all right? So this gives us a better cost model. This is much faster to implement, way faster than doing it that way, if you're implementing a language. I do have a bit of a complaint with this machine. Well, a couple complaints that are very closely related, right, aside from the fact that I didn't bother with environments yet. Well, there's two. So one is there's a bit of an annoying redundancy. Those two things mean roughly the same thing. It's function application. So I have two ways to write function application. And the first rule, which is searching for the actual reduction to apply, is converting from one type to another, right? It can either be an application on the term or an application in my context in the continuation saying what to do next. So redundancy is never great. That kind of bugs me a little bit. But there's a slightly more annoying problem that if you've ever worked with abstract machines, you may not have known this is part of the problem, but it makes your life a lot worse. So when we were dealing with this nice high-level abstract notion of computation, we could very quickly enrich it with very useful theories, right? So even just the rewriting theory. I could say, well, instead of doing the next step, just do reduction wherever you want, right? So we had this arrow, which was the compatible closure of the standard reduction step. So I mean, do it at any context with no restrictions. And now I can start to relate lots more terms. And then we could have equality as the reflexive, transitive closure, or symmetric closure of reduction. All right? So now we can start to talk about when programs are equal. And even without doing fancy type system stuff or even logical relations, we could get a lot done with this, right? Okay, so what if I want to talk about equality over here? So I'm saying, okay, first, do a reduction step anywhere that you find it. Where are you going to find a reduction step? At the top, right? Because these deal with machine configurations. Where else are you going to find one? Nowhere else, right? Because these are all terms. They have terms in them, right? Continuations have other continuations and terms in them, but nothing actually contains a machine configuration in it. So if you want to talk about optimization, right, as a special case of equality, so reasoning about when one or two programs the same, I can do it over here, but I can't say anything really meaningful here other than just, well, run it, and wherever you get stuck, that's what it is. Right? I could never even like reach into the body of a function and simplify it further. So reasoning about these machines, as it stands, is incredibly weak. Okay, so let's fix both of these problems of redundancy. So there's redundancy and a weak equality. That's my complaints. And how are we going to fix it? Well, we can compile our programs, right? So instead of waiting to do this search at runtime, I mean, I can see and do the search ahead of time. Why not? Right? So just apply these reductions all over the place, right? So let's think about compiling from just a regular lambda calculus into a more machine-like language where we've pre-computed some of these steps. We're not going to do the meaningful reductions. These are the actual reductions that kind of are in the source program or that come up as you run. It's just this annoying search. We're going to do that ahead of time. Okay? So I'm going to start, and this compilation is going to be, I'm going to continue to abuse these denotation brackets. So I'm compiling from lambda calculus to a new machine language that will figure out what that is. Okay? So, like I said, I'm going to keep things super small so that we don't get lost in too many other details. So there are 3 cases because our lambda calculus is ridiculously small. If I see a variable, a lambda abstraction, or an application. So these are the 3 possible terms of just the simple lambda calculus that I could see. And so what am I going to turn them into? So variable, what can I do with the variable? Not much, right? So variables are going to be plugged in by this substitution for now. So I can't really do anything for the variable. Lambdas. What do I do for lambdas? Any idea? I thought I heard a suggestion. Translate the body of the lambda, right? So I want to translate the code in the lambda. But I don't really need to do anything else here because I see it on the left-hand side of this rule. So I'll leave that one alone. See if that works. So leave the lambda alone. But I should translate the code inside of the function with the idea that if this is also machine code, I can use my machine theory to optimize it. Instead of being like, well, this is code from my source language, and I need to reason about that in terms of the source language and hope that means something in the machine, we're going to put it all in terms that the machine itself understands. All right? And now this is the tricky bit. So I kind of want to say, what does application do? Well, for any k, we're going to push the argument onto a call stack. All right? And so if it's this term on its own, what does it mean? Well, I'm going to call m with n on the return call stack, right? So I'm calling it with n. And then what do I do afterwards? What would you tell someone? Well, you call the function with n and then return its result, right? So let me just be a little naive. So I'm going to say this is M. Well, we need to compile things. So we compile M. And then we push N onto the call stack. And the continuation for what we do after this is over is to return to whoever called us, right? So I'm going to add one more continuation, which is the base case, because you always have to ask, how do I get started? There's going to be continuation return, which means I'm done, return the results. And there's a bit of a sort of type or syntactic sort error or something, but now I had a term, and now I've got this machine configuration in a place where I need a turn, so I'll put just an explicit syntactic marker, run, just to make it very clear that what this means is if I have a machine configuration, run until it finishes and passes a result to return, and then that's the result of this term, right? Because terms return things, whereas machine configurations don't really return. They just keep going until they stop. Right, so this pops out the result of a machine. OK. So hopefully, does this make some sense right there? Make sense, hopefully? All right. So let me now list out the syntax that we're dealing with. OK. So I've got what are my new terms in this machine language? A machine language, right? So my terms, M and N, are what? So I could have a variable. So what's on the right-hand side? A variable, a lambda, and what else? Yeah, I have a run type thing, right? And I think Frank used S for machine configuration statements, right? I'll use S2. Right? So this is an actual machine. It's like a sub-machine. So run another machine and then grab its results. OK? Now I've got my continuations, K. And what could those be? Well, here is a continuation which contains all of them. I could have a argument on a bigger call stack, or I could return. Those are the two things that my continuations could be so far. I can apply a function, or I could return a result. And then the last thing is what is my machine configuration statements. They have this form over here. I've internalized them as a type of term with run. So it's a combination of a term which produces a result and then sends it over to K, right? So K is expecting a result as input, right? It's consuming an input, and then M is producing some output, like a function. We could add in Booleans. It might produce a Boolean, something like that, right? So this is my machine language. And OK, so who cares? Well, the idea is now, whenever I have a function, if my function actually has some steps that I could reduce, that's going to be expressed in the form of one of these machine statements. So for example, what is a good example? Just to make things, and I'm going to do the lambda calculus theoretician's favorite example, the most boring optimization in the world. Right? So suppose I had lambda x. Well, I'll write it this way as shorthand. My identity function is lambda x, right? And then so now my example is going to be the function that takes one argument and then returns the identity function applied to that argument. Right? So I should be able to simplify this ahead of time. There's no reason to do that later. So those rules don't tell me what to do here. Obviously, from the lambda calculus, I know what to do, but those rules don't help. But if I compile the program, what do I get? Well, I get a lambda. And then what's the body of the lambda? It's a run. and I get a little submachine. And what does the submachine say to do? It's going to be the identity function. Well, technically, I compile the identity function. And then what's the argument? Is y. And then what do we do after passing in y? We return. Right? And this compilation of the identity function is lambda xx, if you kind of go through all the cases. So now I can apply a machine reduction step and get down. Right? Does that make sense? So this now matches that rule. And then we plug in y for x, and we get the result. Right? So this now steps to lambda y, run y, and then return. All right? So we can optimize our programs directly, just thinking only about machines, not worrying about how lambda calculus works anymore. Yeah?
Is compilation guaranteed to terminate? What happens if you compile omega?
So is this guaranteed to terminate? So how is this defined? So it would not terminate. So compilation takes one syntax tree, returns another one. We're not doing reductions. And so how is this defined? It's defined by induction on my input term. So every time I use my denotation brackets, it's on a subterm of what I started with. So as an exercise, compile omega and see what you get. X. I mean, you will get a term that if you ran it will not terminate, but the compilation terminates because we're not doing any reductions. This is the one that doesn't terminate. You can kind of say, well, if this is the only reduction rule I apply, I will always terminate. Right? Because I'll kind of run out of things to push on the stack. Right? Lambda x, x, x. See what you get. Yeah?
Do you have to compile y?
Do I have to compile y? So the compilation of y is y, based on the first rule. I just skipped. Yeah. This is the compilation of y. Compiling variables as variables makes your life enormously easier. All right. There's one thing missing, though. It's kind of related to this. I added run to my language. What happens then? Right? So if I extended, I added one essentially new thing to my machine language. I got rid of application, so I don't need this rule anymore. Right? I've precompiled that step away. But now I could hit a configuration like this. I could have a run of some s next to a continuation. What do I do here? Does anyone have an idea? There's a couple of things you could do. One is cooler than the other. Yeah. So replace it with just s. OK, so if I did this, syntactically that's correct, but that means forget what you were about to do. So instead of saying run s, get the result, return it, and pass it to k, k's gone. So this doesn't do the same thing as what our original lambda calculus term was supposed to do based on its specification. An answer I sometimes get is, well, run s first, and then when it's done, pass to k. But then now I've got a stack of stacks, and I'm just making things worse. Yeah?
So S is a machine, so you can take the left side, replace S with M, and then put K on and put a stack in front of the other stack.
Yeah, so I want to mix up the stacks in the right sort of way. So basically say, well, just run S. So this is the right sort of idea. But when it wants to return, every time it wants to return, its result needs to go to K. So rather than kind of have a stack of stacks, I can say, well, just embed K for every use of ret. Right? So, I mean, if you look at these as lists, it's really like list append. If you start adding more cool continuations, it may not be obviously just append, but this works just like substitution does. Right? So I'm replacing the use of ret with K here, right? And only for those that would be returning from this particular submachine. Okay? Does that at least make some sense, hopefully? Some intuition? All right. What's the kind of danger if you're doing this search and replace? is this submachine might have submachines within it, which also refer to ret, which doesn't mean return here, but return from some inner procedure. So we don't want to replace those. So when I say how to replace it, I would say, well, don't do that. And essentially, this substitution is going to stop when you hit a run, because that's some different subroutine procedure, right? So that's kind of the scope of the ret there. OK, so now I've deleted this first rule. I've replaced it with a different rule. And I can run all of my programs. But now I get a meaningful equational theory, right? So I can say that this is the arrow without the tail is the compatible closure of the maps to arrow, and then equal beta. I guess these are all betas. I want to, sometimes I try to be careful labeling equality with beta so that you're not confused what I mean by equality. I mean do beta conversion. And then this is the reflexive, symmetric, and transitive closure of the general reduction arrow, which just means, right, this says apply these rules anywhere. And now I have a bunch of submachines that I can apply it to. And then this says, yeah, go forwards or backwards as many times as you want. I don't care. All right. OK. So now we have a meaningful equational theory on machines. So basically, kind of my agenda here is I want to, all of the cool reasoning that we can do about programs in the lambda calculus, we can do directly on machines. Right? So rather than say, well, I have my cool source language, it's really nice to reason about, and then I compile it to some garbage, which is totally unreasonable. But I mean, if I run the garbage, it happens to do the same thing as my really nice source language. So I mean, I guess that's a fine implementation. And I can't say anything directly about that, but I'm always relating back to the source. And then you end up in this nightmare of constantly doing simulations between these two things, and they get out of sync, and it's not fun. Or you can just say, let's make our machines reasonable, and I'll reason about them directly as well, and then make sure that these two things are equivalent. Oh, by the way, since this has an actual equational theory, that means we get a fun property, which is, I'll say soundness, and completeness. This is from the idea of everything I can do in lambda calculus, I can do in an abstract machine directly, which is that M is beta equivalent to N if and only if their compilations are equivalent. There we go. So the one direction just says all of my reductions in the source machine are simulated, or sorry, source language are simulated by the machine. That's fine. And that means that everything I knew before, I can do afterwards. And then the other direction says that my specification of the source language can do everything that my actual implementation will do, right? So it goes both ways. OK. So I mean, that's neat. Right? So now that means equality is the same in both settings, and I can do whatever I want. So what else might we want to do? Well, what was another thing, right? If we want to talk about if programs are equal, we wanted kind of extensionality principles, right? So this was just rewriting without thinking about it too hard. But you know, we had these problems that if I had functions that are really only well-defined on Booleans and I want to constrain that and use types, that means I have to add types to my machine, right? So let's see if we can do that. So let's add some typing rules for our abstract machine here. And I'll start with the funnest one. Which is, this is like, shows everything off so that we know exactly what we're going to do. Let's cut to the chase, right? So when would it make sense for me to put together a term and a continuation? Well, if the result that the term returns is the type of the thing the continuation expects, that means I have to be able to specify what type of output does M give, what type of input does K expect, and they should match. Okay, so let me write that on the board. I'm going to do this in the French style, which is extremely artistic, so you'll have to bear with me just a little bit, but it makes things look very nice. So the first step, I mean, this is no surprise here. Suppose M returns an A. Fine, right? Nothing out of the ordinary here. I have to specify what does K expect as input, right? And I'm going to write it like this. I'm going to say K expects an A on the input. And I'm writing it on the left. Why? These are kind of my assumptions of what's coming in. Right, so K might refer to some free variables coming in, as well as an extra input that doesn't have a name. That's just what I plug into it. That's what I pass in through that command. And then what does it return? Well, every K has a ret in it, at least. That's what it returns. So kind of on the output end, Ks don't directly return, but they have a outer return pointer that they'll invoke when they're done, right, to kind of pop up to the next layer. I'll say there is, on the right-hand side, a ret. That's my return pointer. At the bottom of my stack, this is what I return. So if I stick these together, what do I get? I get a machine configuration M, or I stick it together with K, and the A's are kind of taken care of. That's internal here, right? There's a communication of A's. I guess it's really from left to right, so let me write that arrow there. Doesn't really pair in the outer interface. But I do see what the final return pointer is, right? And any free variables that could appear in M or K are still free variables of this hypothetical open machine. Why do I need to account for free variables here? Because I could have submachines everywhere, maybe under a lambda. So it's important. I think I had this example, right? I have a free Y. Even if we want to run closed things, the inner deeply nested inner code has to refer to local variables, right? So I'll write it this way. This is a machine configuration that has free variables gamma, and if you run it, we'll send a final answer to that return pointer of type B. Okay? This is a typing rule for machine configurations that shows these are all the three judgments that we'll be dealing with. This typing terms as normal. Continuations, I'm writing the actual continuation itself on the left-hand side. So in a sense, you can think of gamma as the free input variables, return is the return pointer. And the machine configurations, they don't like directly return anything. They run, and they might end up with a B value passed to that return pointer at the bottom of the stack, right? But they don't themselves return. And we'll talk about other things in a second. So what else? I need to access variables, right? And so what's one of them? So if I have a variable x in scope, then, and it has type A, then x has type A. No surprise here. What about the return pointer? So, well, let's do the other term, because that's the easiest one. You should by now be able to tell me this rule. When does a lambda have type A arrow B? When the body M has type B with a free variable of type x of type A in scope. Okay. M has type B. All right, so now these are most of the terms. I have continuations and run to do. So what should I do next? I guess I will do run next. That might be the next most intuitive one. So what about run? So how does run work? So suppose I have run and some submachine. Let me move this down slightly so that there's room. Run with some submachine in it. And suppose it has type A. When does that work? I'll have to say something about what that submachine is. And submachines don't have a type, do they? Not directly, but they have free variables and they have a return pointer in them. So, I mean, sure, it has all the free variables that this term has access to. What does it need to return? So ultimately, I have to return an A, which means the return pointer inside this submachine is going to receive an A. And when it does receive an A, that's what pops out of the run. That's how we know this machine is done. So it will run, we'll have something like run S, well, in some sense, K. Well, how do I want to do this? Let's do it this way. Run S. This is kind of just a principle, is equal to a value V when S is equal to V and ret, just so we kind of get that intuition. If you run the machine and get a value out, we're going to pop that out. Okay? All right? So now there's only two more things I need to explain the types of. Right? So what are those two things? I haven't said anything about the continuations themselves. Okay, so let's do ret itself. So I have to explain what is the type of ret, right? And so what's the form of the judgment? So continuations, their types are described like this. They have and type that they're expecting in, and then they can access, or they can return a result. I have a return pointer of type B. So what is the type of the return pointer in this continuation? Ret. It's the same thing. All right, so whatever you pass to it, that's what I get, is the idea. So these both have type A, and I don't need to explain anything else. So whatever you pass to ret is what you get out of ret, is all it's saying. It's kind of an identity function. And, well, the trickiest one, I'll just write the answer. So what about, right up there, n, m, okay, fine, dot k, ret, I'll allude, there's a b prime there. And a call stack is expecting a function, right, which has some type A arrow B, right? That's a function type. So whatever function it gets, I'm going to pass in m as the argument. So the type of m better be the type of argument that function expects. So it better be that m has type A, and the return pointer that the function returns to is going to be of type B, so that better expect to be. So gamma k has type B, and then the final outermost return pointer has some type B prime. Okay? I'm just saying that's the rule. And how do we know that these are the correct typing rules for the machine? All right? So what would be a check? So if we get type safety, all right? That's one way to check that the operational semantics is somehow in sync with how I type check the terms, right? That they prevent me from getting stuck. And so with these rules up here and these typing rules down here, you can prove type safety. How? Well, we can, certainly the easiest way is progress and preservation. So I think Frank mentioned in his last lecture that he had a similar sort of machine configuration type system, and that you can do progress and preservation for that. You can do progress and preservation for this, which is telling you you never get stuck, and each of the reduction steps don't change, in a sense, the typing of the machine configuration, which basically means our return pointer is still going to get something of type B, and our free variables, we expect the same thing out of them. Okay? Now the fun part. So this is the type system for this little abstract machine language. I never wrote any. We normally label our rules so we can refer to them. So what are the names that I should put for the rules? So some of these you've seen before. And some of them you've seen before in a different form. So what about this one? What does this rule look like? And when I say look like, delete all the program bits. So forget about M, forget about K, forget about this machine configuration. What does that rule look like? Does anyone remember from Frank's lectures? What was that? App. That's one option. And we kind of would have to assume that this K is like a function. But that's not a function. This is an entailment arrow. There's another rule like that. What was that? Call? We didn't have a call rule. Cut. So there's no function arrow in cut, but I have something to the right of the turnstile and the same thing to the left of the turnstile, and then we delete it. So this rule is cut. Well, what about this? I mean, this is just the variable rule. What is this? I mean, this is just the introduction rule for functions, right? I'll write it this way. It's the introduction rule, but, well, notice that it works. So did Frank explain what intro in a lim means, or does everyone kind of know? So intro means I've put a new connective below the line that wasn't above. All right? A lim means that there was a connective above the line that wasn't below. So I'm saying I'm introducing, and I'm introducing on the right because this arrow appears on the right. And why is that now important? Because I have this rule over here that it's not a lim rule, is it? Because the connective arrow doesn't appear above the line. So this is also an intro rule. But where do I introduce it? On the left. All right, so I introduce on the left. OK. I have two more rules, but let's focus on these. So intro on the right, intro on the left. And you've kind of seen this, I'm sure Frank has talked about in the sequent calculus. You've got left and right rules instead of intro and a lim. Another way I like to think about it is that sequent calculus only has intro rules. And for this to be interesting, some are on the left and some are on the right. Natural deduction or lambda calculus only has right rules. And to make it interesting, some are intro and some are lim. Right? So we have this kind of quadrant of, intro. Well, I'll do left, right, elim, intro. Right? And so this is natural deduction, and this is sequent calculus, right, of the types of rules that we could have. OK. I've got two more that I should probably name. This one looks a lot like var if I forget the fact that this is x and that's ret. And I forget about this vertical bar. I just make it a comma. It's like another axiom rule. All right, so I'll say this one is covar because, well, it's the opposite of that because the main thing, instead of having a term on the right, I have a continuation on the left. But otherwise, I do exactly the same thing. Right? And this alludes to the fact that ret, and I'm using substitution instead of saying like list append, generalizes to other sorts of systems. But that means that ret really is, it acts like a variable and has all the same kind of properties that a free variable x does. But it's for continuations, hence continuation variable, rather than regular terms. And then there's this last rule that doesn't have much of a logical meaning if we delete a lot of punctuation in programs. I just say, if I can prove A, then I can prove A. This is more a kind of structural type of rule that I'm mediating between a kind of refinement of different notions of what it means to prove A. And the traditional name for this is activation. So I'll write act there. It's not logical in the same sense as it is about a connective. It's about the structure of judgments instead. All right? But we kind of need that to go between these two parts. OK, question, yeah.
So in all the rules where you have right on the right-hand side,
Yeah.
it looks just to be syntax of the judgment. But so maybe you need to write it. Or is there another way that you would put something else there instead?
Excellent question. So that's alluding exactly what I'm about to do. So I do need to say something about it so that I know what to expect. So if I deleted it here, for example, then when I run this, I would just say, well, I have some free variables and I have no idea what comes out. So when I run a subcommand, oh, and it's, do I need ret on the right-hand side? And second, can I replace it with something else? So I'll need to know what pops out here. So I need some information. And because like this could be way deep inside the continuation, it's not obvious just by looking at it. So I need to propagate that information up. What is that final return pointer? And that's why I write something there. But do I have to write this? Or in particular, I mean, if that's a variable, and this is kind of like, well, I have a bunch of free variables on the left with various types assigned them. And I have one free variable on the right with one type assigned to it. Why do I have to have one here? What's forcing me to have just one thing instead of a bunch of things, right? So now I'm going to start adding some more stuff to my machine language, but not too much. All right, and what am I going to do here? So basically, the main idea is that instead of ret, I'm going to say, well, sure, you can say ret, but I'm actually going to have a bunch of these things. So there's going to be a bunch of variables I could refer to. So instead of one return pointer, why not a giant pile of return pointers, just for fun? This could get a little confusing. And so I'm going to use the syntactic salt to help distinguish. When I say x, you'll know, is this like a term or is this like a weird continuation thing? I'll put a little twiddly on top. There's a little twiddly here. OK, so that's part one. So now I have a bunch of these. Right? So not just ret. I can have like ret1, ret2, ret3, or I don't know, exit and blow up, or finish the program, I'm done with main, right? There's kind of a bunch of these things. Weird alternate exit paths because an exception happened. OK, so now I have a bunch. There's a bit of a problem. When I say run, it kind of gobbles up an output and returns it. And I only had one option. So I didn't really need to say anything more. Just like run it, and then you will return, and then that is the output. But now it could be, return or like exception. Which one am I looking for? Exit 1 or exit 2. So it's not enough to just say, please run it. You have to tell me what you're looking for. And I'm going to now use the traditional notation, which I'm sorry, it's a mu. This has nothing to do with recursive types or even recursion. You can blame, this is from the lambda mu calculus, and then specifically the one that I'm doing, and I also apologize for this name, is lambda bar mu mu tilde. We'll get to the mu tilde later, in case you want to look this up. These are not the best names. Oh, this name is fine. It just used mu, which is already kind of used for other stuff, so it's a little confusing. So you have to context shift here. I'm not going to talk about recursion or recursive types at all today, so don't ask. OK? But so I'm saying, what am I looking for? So you have to tell me, what output channel are you trying to gobble up and return as the result of this term? All right, so I have to name what I'm looking for. So let's update these rules. OK. And I'll update them incrementally as we go. So I think that's all I'm doing for now. Well, for now. OK, we'll do one more change in a second. So the main point is I could have a bunch. So I'm going to use delta on the right-hand side to say all of the possible return pointers that I could refer to. And among them, I've got one, which is going to be this output channel x with a twiddly mark on it, and therefore x with a twiddly mark on it is a continuation expecting an A, right? Because I'm saying if this is an output channel that only accepts things of type A, so it's going to send that to the outer world, then I can use that as a continuation as long as I pass it A's, because it's going directly to the outer world. All right? OK, so I have to update now run. Right? So run has to specify which output channel it's gobbling. So what does this look like? So I'll have a bunch of other ones This is saying if a machine configuration can run and pass an output to a bunch of different things, one of which is X with a twiddly over it, if that one is going to receive an A, then I can run that as a subcommand. And if I happen to get an output on that X, I'll return that and I get an A. Otherwise, an output might go somewhere else. So that's what this delta is keeping track of. All right, do I have space anywhere? I'll write it down here. So just to kind of make this clear, our gamma is, as usual, a list of types assigned to regular variables. Right? That's what we expect. It's just a list of type assignments for variables. Delta is going to be a bunch of type assignments, but to covariables. So structurally, it's the same thing. It's just on the other side. That's just a big list. For each output channel, what type of thing does it expect? All right? So when we're typing terms now, right, I'll have the main output channel, which is the term might just return, or I might send an output somewhere else. That's the idea. So let's update. There's a few more rules to go. Let's do this general case here. So a term n might return normally with an A, or send an output somewhere else. And this continuation, well, it's just going to have a bunch of, it never really returns, but it will send some output somewhere to the outside world. Right? And this kind of like gets rid of this really annoying clunkiness, right? Instead of always saying ret has type B on the right-hand side, I just kind of replace it with a delta. Does that make sense? Just generalizing, anytime that that's not the main focus, it's just, well, I could have a bunch of them, right? So let's now update that one. Let's do the familiar ones. So X definitely returns something of type A and doesn't actually use them, but you know, they could be around, they could be in scope, I just don't use them. A lambda, which is kind of sticking it around, this is extra information. Kind of like when we did adding type variable generics, you just kind of thread it around if it's not relevant. And then the last one is this most confusing one, which is the left rule for the implication arrow. So we just replace that with a delta and then say that the delta could be used here. Okay? Does this make sense? It's kind of updating. Any time that I said, well, there's a free return variable ret on the right-hand side, I'm saying it's a list of them. And as a special case, this list could be 1. Right? So I'm generalizing what I had before. So this could always just be 1, and then it's exactly what I had in my original system. All right? Question?
In the variable case,
Yeah.
do you require that like delta and gamma have like the same types in them? Or just pick one?
Different types, different sizes, different names, not connected at all. So they're not relevant. If I was in a linear logic, I would just not have them. They'd be empty. So this is just a way to say, it's like weakening. I think Frank has mentioned weakening before. It's saying, the most specific case is that X goes to X of the same type. And then we can like add other free variables that I'm not using, and I can add other output channels that I'm not using. And it weakens the statement, because I'm saying, theoretically, if you don't see this, you're like, well, I mean, it might return an A, or it might do some other stuff, but then if I reveal it's just X, okay. It returns an A. I know that just by looking at the program itself. Okay. So that's the first. This is the sequent calculus. So mentioning with one covar ret, this is equal to, I'll say isomorphic to, a system called LJ by Gensen. This is one of the first sequent calculuses, right? Invented when we also had natural deduction. So the same paper invented both natural deduction and sequent calculus. So the original system I wrote on the board was just one return pointer. It's called LJ because, well, it's an acronym from German, and this was his intuitionistic sequent calculus. So many covar is equivalent to LK, and K is German for classical. So this programming language, this machine language, is a language for giving a computational meaning to classical logics, right? And so it may not be obvious just by staring at these rules. We can now write more programs than we could have before. All right, so what I could write before was really just the image of functional programming languages. And there are certain properties of classical logic that you cannot possibly write a purely functional program for. Does anyone know some of them? What are some famous ones? Excluded middle is the most famous one. So let me put it here. So excluded middle. So we can have A plus, and I'll write it this way. We didn't talk about negation, which is a little tricky. So one exercise is add plus to the system to do this one. And you can use the notes to kind of figure that out. But also, A arrow B is kind of like negation in the sense that if not A is A arrow false, and B could stand for false, saying arbitrary A and B. Either I can prove A, or I can prove A implies an arbitrary B. So that's like false, and I do X false, so code the bet, which means from false I get anything. You could add a bottom type 2 if you want, if you really want an extra challenge. But this is enough to get things going. So there's a lot there. There's another one, right? So A, and I'm doing the same trick here. Not A, which I can kind of write like that. This is like double negation introduction. And hopefully you believe you can write this program. How come? I give you an A. I give you a function A to B. And then you have to give back a B. What function is this? App. So try writing it in the machine language. It's some good practice. But then what about this? A implies B implies A implies A. This is similar to double negation elimination. It's called Peirce's law. Not Benjamin Peirce, a different Peirce. But this is not a theorem of intuitionistic logic, but rather classical logic. Yeah?
So for this third law, it's
Yeah.
A implies B implies A, which is, I guess, notably not symmetric to the one right above it.
Yeah, if you want to do the symmetric one, then you would do basically write A. I mean, you could do A implies bottom, for example, and then you have to add a bottom type to your language. And then you would do A implies not A, and then not A implies A. So this is purely functional. That one's not, but you can still write a program using that type system. If you add some more connectives that I'm not kind of explaining here. Yeah?
Can you talk about, explain like the interpretation of that as call CC in the context of these abstract machines, or is that separate?
You can. I will not do it here. You should look at the videos from 2022 where I did do this slower. I just don't have time to go through all of that. I want to do something different this time. But yes, this is call CC. This is the type for call CC, if you know what that means. OK, so I now want to pivot and do the cool thing, right? So that's classical logic just by having multiple return pointers, right? And that's often a thing that I think of that if we're talking about these kinds of logics and I have judgments, and so you'll kind of see I wrote my continuation's kind of funky just to keep inputs and outputs straight. Inputs are on the left, outputs are on the right. And so intuitionistic systems always have exactly one thing on the right, period. Classical systems can have 0 or more things on the right. It's kind of weird that that's the case, but I mean, that's from Genson's original paper where he defined LK and LJ, and he kind of noticed this immediately, almost 100 years ago, so that's kind of neat. I also like the fact that in the 1930s, Genson predicted the typing rules for function call stacks in computers way before he had computers. So that's kind of cool. Anyway, let's do the neat thing. And I will put it here. Wait, no, I need some more stuff. So what do we have at this point? Well, I'll write it a little bit differently now. So at this point, what do we have? We have variables and covariables, and they're now kind of in sync. They have equal expressive power. And what do I mean? Well, I can refer to them, and I have as many as I want, and they kind of obey the same scoping restrictions. Oh, I should explain my rule here, but this one's less of a surprise. I'm telling you where the output is going to go, so substitute for that one. So like I wrote it this way because nothing changes. You immediately get this really neat interpretation. Okay? So now I want to kind of complete this duality. Right? So if these two things are equal and opposites, can I add the rest? Right? So what does that look like? Well, let's see. I need a little bit more space here. I'll move these down, these machine states. So this doesn't change at all. This is still sending m's that produce results into k's that consume them. And now I need some more stuff. And what is that? So I have a variable here, corresponds to a covariable there. I have this weird thing, which is run a computation. And when it sends an output to x twiddly, that's the output of this term. So what's the opposite of that? A continuation that runs a computation after you give it an input, and we'll call it x. All right? So that's what this is. So basically, I've moved the twiddly from the variable to the binder. Say that these two are opposites. And so this is a continuation. And this, when we think about and talk about continuations, if you've ever done continuation passing style, right, the continuations are like a lambda or a function that takes an input x and then does stuff. And that's the rest of the program. And that's what I'm writing here. Whatever the input is, let's just name it x and then do some more things. So those two are opposites. And my goal, where do I want to put this? My goal is to define, here we go, a duality relationship that for every term I can have a mirror image. So basically I want to exchange the roles. So what is this duality? If a term returns input, k accepts it, then I want to swap them. So the thing that was consuming information is now producing it, and vice versa. Right? That's the trick. So the main kind of driving idea of this duality, so I'm writing my duality operation as a superscript bottom in honor of kind of Girard and a lot of these duality negation things. So I'm going to swap them. All right, so I want to put the consumer, what was the consumer on the left and what was the producer on the right. But this doesn't make any sense, does it? Because they're the wrong sorts of things. So we have to flop those as well. So this is like the founding principle for it to work. And it's plausible because I had these variables. So what's the opposite of x? It's going to be x with a little twiddly over it. And the opposite in the other direction is going to be just x. So it reverses each other, right? So if I do, and this is a thing to prove, which is, this is the easiest part. This is actually kind of the cool thing. Like, you think this is the hard part. No, it's just like, you do an induction, and it's basically trivial. If I do this twice everywhere, then I get back the same thing without doing any rewriting or math. You just go by cases, and it follows. M opposite opposite is M. K opposite opposite is K. This is known as an involutive operation, which is if you do it twice, you get back to where you started. It's just like negation, right? So negative negative 5 is 5, is the idea. OK? So these are variables. And I concocted this, actually kind of the more familiar thing. So this is like a let. So intuitively, you know, if I have M and this little twiddly mu x dot s, this is essentially saying let x be M in S. That's, for functional programming, that's how I'd write it in that style. It's just a binder. OK? So that means the opposite of the mu is the mu with the twiddly over it. So like I said, I'm moving the twiddlies around. And then the other way if I take the opposite of a continuation binding its input to x, then that's the same thing as a computation that binds its main return channel to x twiddly. And then I have to opposite the middle. Okay? And now I have kind of the two other parts. What do I do for a lambda? And then what do I do for the call stack? So I have an M, and I have a K. And what's the opposite of this? Right? So these are all continuations and terms. And then these are all terms, continuation. So the opposite of a continuation is a term, and the opposite of a term is a continuation. So what do I do here? And, well, my advice at the start of what should I do is just be a little naive. So this is a pair of two things. It's like a really weird tuple, a tuple containing a term and a continuation. So let's just say that that is the actual term. It's going to be a tuple. Let me write it using slightly different notation here of M. What do I do here, just so I remember the order? So if you look at the notes later. Yeah. So M, K. So this is a tuple of two things. This will be a continuation, and this will be a term. All right? And that means this. And so I can add that as one of my missing terms. So this is going to be a continuation and a term. A pair of those two things. And then I need the opposite of a lambda. So this just twiddlifies a bunch of stuff. So that means I'm going to have a twiddly lambda with a twiddly variable. And then we take the opposite of this. And so what will this be? A continuation. So this is a function on continuations. It says, give me some continuation channel in, and I'll give you back another one. And then I have to go the other way to make this actually well-defined and involutive. So if I have K comma M, the opposite of that is K opposite dot M opposite, and then the opposite of a twiddly lambda is a regular lambda. Okay. So I won't have time to spell it all out. But so far, this is just purely syntactic. I'm rewriting two syntax trees, and it's like, OK, fine. You're just adding twiddlies and you're deleting them, whatever. That's not the cool part. This is the setup. The cool part is that we can define two different semantics here. So this is call by name, right? So I can also define a call by value abstract machine now that I have the twiddly mu. And it turns out that there's another theorem which says if I have a reduction step in call by name, then, or I'll say this, if and only if, the opposite of S takes the same step to the opposite of S prime in call by value. So I know Frank has mentioned, oh, well, this thing is like call by value or eager, and the other one is lazy, and they're kind of dual in some sense, and this is formally how they're dual in terms of those rules. So if I flop the input to output or the flow of information in my program, then quite literally call by value is exactly dual to call by name in the sense that they simulate each other exactly on the nose on a step-for-step basis. OK. So I know we're kind of near the end, so I'm not going to introduce much more technical material, but there's some exercises here. In particular, figuring out what to do for these two things. So I had function types. So what is this? So typically people represent this as a subtraction type A minus B because I have an A and I need a B. So it's the presence of A and absence of B, right? If we kind of think of these as set operations. And so you can give typing rules and reduction rules for those, and it's just take this and swap the two sides, right? So you just swap the two sides and twiddlify things, and that's all you get. Same for typing rules. But why does this matter? So this is like a cool theoretical result, but why does it matter? So I want to focus on that in particular, that line. So I know a bunch of people in this summer school so far have talked about things like representations of values and unboxing and flattening stuff, right? So we don't really want this, right? A pair. We want a sequence of 4 things all next to each other in memory, right? And I mean, this is not a new idea. Compiler writers have been doing this for a long time, right? And a particularly nice one is kind of the way GHC has been doing this since 1991, basically. So for Haskell, Glasgow Haskell compiler, there's a paper that talks about unboxed values as first-class citizens of how do we deal with these sorts of things. And we want to have flat layouts of things. And if these are floating point numbers, we want floating point numbers in floating point registers to do really fast math. Otherwise, things are horrendously slow, right? For a long time, GHC has had unboxed numeric types that live directly in registers, unboxed tuples that ideally are just a sequence of registers holding values, right? And at some point, I was staring at this equation, and I said, well, if we kind of squint a little bit, if I have unboxed tuples, what is an unboxed call stack? What does that even mean? What does that give me, right? And so the answer to that question, right? So if I kind of write that down, the answer to that question was that paper that was mentioned on maybe Wednesday night, kinds are calling conventions. And it's kind of related to that question that, currying is kind of a farce and it's ridiculous and no program should actually run curried programs directly. So can we have types that look like they're curried types, but in reality, right, if I say A, arrow B, arrow C, I actually mean pass A and B at once in registers if possible, and then get a result of type C. This is not too hard to do if everything's monomorphic, but once you add polymorphism, everything gets very challenging, and that's mainly what that paper was about. And I also want to kind of mention, well, and this is why the theory is really important. So that paper builds on some previous work. Like I said, there's the unboxed values by Peyton Jones. And Launchbury. And then more recently, there was a Levity polymorphism by Eisenberg and Peyton Jones. And then this paper was a follow-up of that. One of the challenges is actually getting this to work. We need a lot of very rich type information. This only works for type programs. And there's complicated questions of, when can we have polymorphism when stuff is unboxed? So like the identity function, I need to know where you're storing the argument. Like which register is it in? So that needs to be kind of part of the program. And compiling these programs destroy type information. So that's really unfortunate. In this upcoming ICFP, I've got a paper coming out called by Unboxed Value, which, and so this is going to be ICFP this year, which someone posted on the Slack that there's these kind of two ideas. There's call by push value, and then there's focusing and polarity. And they're almost exactly the same, but they're not. And that's really frustrating, and it's bugged me for like over a decade now, probably. So at some point, I'm like, well, if they're not going to be the same, what happens when you combine them? And then what you get is a proof-theoretic, kind of much more principled combination of things that you can use to represent these unboxed representations of things. It kind of scales to other stuff. We can have unboxed sums, and then they fuse in very nice ways. So that's something that's coming out. So there is, like, kind of looking at the theory does give you very nitty-gritty compiler stuff. And then, like I said, is the other reference. Right? Or is it abstract machines and classical realizability? So in 2022, I also gave some OPLSS lectures on abstract machines and classical realizability, which connects all this stuff to logical relations. So just like I did a logical relation, and Mal did lots of fancy logical relations for lambda calculus, we can do that for these two. And the key words to look for are biorthogonality and top-top closure. So you get a lot of really interesting structures that involve subtyping and inductive and co-inductive types from that. And so I have no time to talk about it here, but I can point to some past lectures where we can look at information for that. So that's it. I'm at time now, and I want to make sure there's enough time to go take a nice photo. So there you go.